Hello, and next we have Taeber Rapczak talking about A2, a programming language for the Apple II. So I'm going to turn it over to Taeber. Thank you very much.
Thank you. All right, I'm happy to be here with a live audience. So I'm going to go ahead and ask some questions of everyone. How many people here are programmers? Oh, okay, maybe about half. Written some 6502 assembly or familiar with the registers? Okay, about half. Maybe, yeah, I see a few online there too. And any C, anyone familiar with C or any kind of C++? Sweet, about the same. All right, well, a little bit about myself. I'm Taeber. I'm from Florida, and you can always tell if someone is from Florida because we'll let you know like within the first 30 seconds of meeting us. It doesn't even matter the context. You could just be asking our name or telling us, don't run into that building, it's burning. It's okay, I'm from Florida. Anyway, at home, I'm a stand-up comedian. And I should clarify that I do mean in my house. I've never actually been out and done any stand-up or anything remotely comical, although I do have an hour-long comedy special on Netflix, so check that out. No, in all seriousness, I'm a software engineer. I graduated from the University of Florida there in Gainesville. Go Gators. I've always had an interest in programming languages and compilers, and I recently found myself with a few free months of time, and I figured, you know, if I were ever going to write a non-trivial programming language and a compiler for it, now would be the time, or then would be the time. You get it. Okay, and yeah, so my journey with the Apple IIs began early in life. My father had an Apple IIe. And he's blind, so he had an Echo, I think it was, or a Cricket that would actually synthesize the speech for it. So it was really neat. And about 2019, I was really getting into retro computing and watching videos. I picked up assembly lines, Chris Torrance looked there, and just read through it all. And I was really inspired to write an assembler. It's written in Go, it's A2 ASM. And that's put it up. Once I got it working on, or got it to assemble correctly, all of the examples from that book, I posted it up on GitHub. So then more recently, you know, when I had the free time, I thought a compiler for this platform would be interesting to write. So now with any language, we have an obligatory first program. If you know anything about programming, which most of you do. And it states, when presenting examples of any computer language, the first program shall be one that prints the words hello world. And you can go ahead and look up that RFC. You won't find anything, but I mean, you can look it up if you want. So A2 is actually heavily inspired by C and a little bit of Golang. So I took this example from the C programming language book. So Brian Kernahan and Dennis Ritchie gave this first example, and the first chapter is basically just going through the syntax to kind of show off the simplicity of the language, and then the rest of it's expanding on that example to kind of show off language of to show off features of the language. So I figured we do something like that here and kind of go on a journey of how we can print hello world to the screen. So this is A2. It looks kind of similar. You know, it's simply declaring a subroutine, and we're calling print line with the text hello world. And if you go run the A2 compiler, you can run A2 compile hello.A2, and you'll, right, yes. So we don't actually have a standard library yet. And I feel like, you know, when I'm thinking of programming and creating a new language, this quote from Carl Sagan comes to mind from Cosmos. If you wish to make an apple pie from scratch, you must first invent the universe. And really, a lot of languages, hello world examples, while they are accurate, they're a little misleading because to truly print, you know, hello world to that screen, like someone has to implement that print function, whether it's like a library writer or the compiler, you know, written into the compiler itself. And actually, as a side note, Oliver Schmidt, who, you know, presented the A2 stream, if you're using C on the Apple II, you're probably using CC65. And, you know, I think he wrote the libraries for the Apple II specific part of it. So you have him to thank for not having to rewrite printf every time. Okay, so let's start simpler. Let's go back to just trying to write hey on the screen. And if you fire up your Apple II and write, maybe use Merlin as the editor and type this into the assembler or the editor, assemble it, and this will actually print out hey on the screen. And we make use of, even though it's not really a standard library, every platform has some built-in functionality here. So I highlighted the count equal FDED, and this actually just points to the heavy lifting done by the count Apple monitor subroutine, and it outputs a character. It lives in monitor ROM at location hex FDED, and it expects the character we want to pass in to be in the accumulator. So that seems very useful if we're trying to write our own print line subroutine. But two questions come to mind. How can we call this subroutine from our new language, A2? And are there other helpful Apple monitor subroutines just out there that we could use? To answer the second question first, yes, there are. I didn't realize this when I was first getting started, but if anyone's interested in getting started with assembly programming or programming in general on the Apple II, here's a couple resources that I use all the time. I mean, we have the Apple II monitor ROM commented, disassembled and commented. You can go right through the source code for it and know exactly what's going on. So just want to put that out there because, again, I didn't understand how any of this worked when I first started. Okay, so we can write hey to the screen in A2 by just doing this. Yes. So this first line here, but that really is just one line. I just broke it up so you can see it on the screen here. So that would fit. Or you could write it like that. I mean, there's no white space isn't important like it is in Python. But let's see. This example shows how to declare subroutines that are external, and they always take the form of use name : type. And subroutines can have input parameters and output parameters. So here we have one input parameter, and to show that it's an input, we use the left we prefix the parameter list with the left arrow, and to signify that it's output, we use the right. And since some subroutines don't have these, they're optional, they can be omitted. And yeah, binding is something that's kind of unique to this language. I don't know if there's another language that does it quite like this. Basically, when we say at $ or at hex FDED, we're actually specifying that it's bound to that address or that location in memory. And another source of binding is register binding. So you can see that the char parameter there, this ch char parameter, is bound to the accumulator. I'm going to talk more about that later, but the next part is to actually then to call count from A2. It's very similar to C or many other languages where you just...
Recording in progress.
Good to know. You just call the subroutine, and then in parentheses, we pass in the argument list. And I guess another thing to point out here is, with the character literals, instead of the single quotes, I just prefix them with the backtick. So that's just a little deviation from C. But that produces, yes. So this is what the compiled code looks like. And all compilers take some source code and translate it into something else. In A2's case, we're taking the A2 code and we actually write out assembly. And then we have a separate assembler, the A2 ASM, that actually produces the machine code. So all of it's kind of like a compilation tool chain. But anyway, so this is what gets printed or outputted. And I tried to color code, what matches up with on the left matches up with the right. So you'll see here the declaration actually just goes down to that count equals FDED, and then the call to count, that first one, cout. You can see it in blue here. We have the load A, load the accumulator with the high ASCII H, and then we can jump to that subroutine by just saying JSR count. So this is what the compiler does, and then similar for the other ones. So this is great. We can now call existing ROM subroutines, but there's 40 plus years of code, of assembly that's already out there. And, wouldn't it be great if we could just call that from our A2 and not have to rewrite a lot of this functionality. So this example is from a 2017, CompSys Apple II discussion that resulted in a very impressive 33 bytes. You don't have to read it. I don't actually even know what's going on with all that. But what it does is it'll take the input. So if you pass in 1, 2, 3, 4 in hexadecimal, it writes out to the screen 4660. So they went back and forth. Mike, Jay, and QCombo went back and forth, and they really hashed this out, made something great. But I don't think I could do any better. So I just want to use that functionality. I don't want to have to recreate it. So the important parts of how to take an existing code base like that and use it from A2, we really just need to declare that this exists, and we have to let A2 know that what the structure of the subroutine is. So on the left here, we have the documentation, and you'll notice there's been some changes in the name. It was dec print, and it ended up becoming dec print U16. But essentially, the input parameters, it's taking the high byte in the A, the accumulator, and then the low byte in X. So the A2 equivalent, the comments, I guess I should mention, comments are semicolon prefix. But then it's very similar. So we just write use dec print U16. It's a subroutine. The high byte's in X, and then the low byte is in A. So then when you call it, you can just say dec print U16, 12, and then 34. I was hoping someone would point out that there's actually a discrepancy in what I just wrote, because the comment there, has the accumulators or the parameters switched. And this I'm highlighting because it was actually one of a big motivation for me. Not that this is wrong. Like, I've had code and gone stale. The documentation goes stale, and I messed up my documentation all the time. So I'm not saying like, oh, this is bad code or anything like that. Totally have done this, made this mistake. But they've in the code, they actually swapped the use of it, I think, to save a byte, and just didn't update the documentation there. However, with compile time type information, if you want to switch the X and the A, where the high byte and the low byte go, you can just do that there and then recompile the code, and it handles loading into calling the right load operation. So you don't have to then go through all the calling code and switch load A and load X. And yeah, I think that's all for that. And there's actually this is so common, the unsigned 16-bit number is so common that there's a built-in type for it in the language. It's called a word. And you can bind it to a, I guess, pseudo register, or, well, if you want to think of it, you just bind it to 2 registers, the X and A. So that's actually another equivalent way of
recording in progress.
Of writing.
Sorry.
It's fine. And then you don't have to actually pass in the bytes individually. You can just pass in the 16-bit word. So let's take another example. This one is filling memory with a value. It's memset. It's from the DOS 33FS utilities, Vince Weaver's. And this basically just fills memory with a certain value up to a certain length. And I guess I'm pointing out here that the documentation style is different, and it's different from the previous example, and also different from how I just described cout. But we can, basically the value that we want to write is going to be in the accumulator. The length of the amount of memory that we want to write to, the span of it, is going to be in X. And then we have the special address, where the mem pointer low and mem pointer high is going to be in 2 locations, which I looked up, but trust me, it's in E7 and E8. So what's interesting about this example is how I wrote the adder. I said that I declared it as a byte up in E7 and E8, but then I can almost cast it or redefine it as a word. So memset now expects an adder which is a word at that location. And so that's an example of how we can not only bind to registers, but you can bind parameters to specific locations in memory. And then this final example of when I'm calling it, I also added support for named arguments. So I'm used to the memset function in C, which expects this the destination or the address to go first, and then value and length. And so, and sometimes that's more readable too. If you just want to, it's kind of self-documenting. Which parameters what and what values what. So yeah, I think I got everything there. Anyway, so I've kind of taken a detour. We're away from our Hello World example, but this was actually kind of the main motivation, because I was writing a lot of assembly, or when I wrote assembly, I wanted to reuse other people's code, and I found that the comment style was inconsistent. I mean, everyone has their own ideas of how that should be documented. And I think maybe the more important thing, even if we're not going to use the language at all, is just this idea that, having a consistent way to do signatures gives us a couple things. TypeScript actually did this for JavaScript, where you can add information to existing code, and Java docs, it's more aligned to if you can add documentation and comments that then a separate utility can go in and kind of, it can parse it and then make some conclusions based on it. So I guess just imagine if an assembler adopted this standard of A2 subroutine declarations. It could tell you if a call to that within the assembler without any compilers being involved. It could tell you if you're loading a value into the wrong register. It could tell you if you're going beyond the bounds of an array. So I think that maybe the most important part of it. But anyway, let's go back to the example of just printing a line. So we have here print line, and now we're gonna figure out what it is. So we know we want to pass in text, but I haven't told you what the hello world is actually going to be, which introduces us nicely into text literals and arrays. So just like in C, the double quoted delimited sequence of characters is, well, in C it's called string literal. I call it a text literal, but it is a sequence of characters. And just like in C, it is null terminated. So here hello world is actually a character array of size 13. And it's a little different. I wouldn't recommend, the syntax is different. Let me start there. So there, obviously, instead of square brackets, if you're used to C, I just use a caret to separate it. And then to access an offset from the beginning of the array, I use an underscore. So that does mean you can't use underscores in identifiers, but I don't know. I guess that's just a syntactic decision I made. What else did I want to say? Okay, so this actually, the compiler, even though this is technically legal, I don't know if I actually want to support it in the compiler, because what this is doing is we have 13 bytes, and it would actually copy the values, those 13 bytes, every time you make this call to print line. And you can imagine if you're passing a text that's, I don't know, 16K or 32K or something ridiculous, you don't want to copy that all around just to make a function. So we introduced pointers. And just like in C, they're just a level in direction. It points a value to a value in memory. But we also have so the memory address is stored as a word, and again, that's that unsigned 16-bit value. So you might be noticing here the syntax is similar to an array. It just doesn't have a size on it. That's why arrays always have size values. It's required. It's to distinguish it from a pointer. But I also know that there's a problem here where the 6502 has a memory addressing mode, the indirect index mode. Yeah. So unlike other architectures, the 6502 really doesn't. It requires you to have your pointers in zero page, and usually that, I guess I could be wrong, but in the language kind of reflects this, where you can have pointers, but you just have to be explicit about which zero-page memory you're taking up. And that's kind of, I wanted people to be explicit so that you're not like clobbering, maybe like an AppleSoft routine or something like that. It makes no assumptions. There's no runtime. It's a 0-byte overhead. And the trade-off to that is you have to just be explicit about where you want this variable to go. And when you do that, you get the benefit that the compiler knows to use that indirect index mode, and it can lead to more efficient code instead of having to copy values and modifying them and then copying them out. Okay, So here it is, our print line definition. I'm going to go through and all this is doing, if you're unfamiliar with print line, we're going to go through all the sequences of characters and just write out cout. So definitions take the form of let name equals something, type, subroutine, number, but they cannot be changed. They're not variable. You could call them immutable. And unlike variables where you can have assignments. And then a subroutine definition without declaration, all that means is just like in C, you have to declare things before you use them. But there's a convenience here where if you define something before you've declared it and before you've used it, that's okay. There's an implicit declaration. So normally you'd have to say use, but here you can just define it. And then variables. Variables are just like other declarations, except they take the var. They can be bound, like we've seen before with to registers or to a specific location. And if they're not bound and they're in a local subroutine, I said they have static lifetime, and that's kind of a term from C. But what I mean is that they persist through invocations of the subroutine call. So if you call print line, well, this is probably a bad example, but if you call a function foo and it has a variable bar and you set it equal to 3, the next time unless you're resetting it or reassigning it, it's going to maintain that through the next time you call.
Recording in progress.
Foo. And that does mean, maybe this is a little too technical, but that does mean there's no general support for recursion, which I think accurately reflects the 6502's lack of support for general recursion. It doesn't mean you can't do it, and recursion is just calling a function from itself. It just means you kind of have to manage the stack explicitly yourself, so the language doesn't kind of help you out with that. And then the next line, the I $colon equals 0 is how we do assignment. And down there, you can also see how we do arithmetic assignment. And that's just plus equals. There's also subtraction. I think the only real thing to note here, I know I'm kind of running low on time. The only real thing to note here is it's kind of annoying. I decided to only do this form of the plus equals and minus equals. The underlying, 6502 has operations like add with carry, and that expects, everything to be done through the accumulator. So this kind of reflects this idea that you have a value, you're starting with a value, and then you're modifying it. So I reflected that in the operations that are built in. There's also, logic and exclusive or, and, or, but there's no multiply and divide. Again, this could be a library function that gets written, but there's no built-in, support for that. I'll skip that part. Okay, and then loops. So when we want to repeat operations like going through a sequence and doing a number of things, of course, looping is very necessary for that. So unlike other languages, there's only one kind of loop. This is just to keep things simple. It's spelled while, and you always have to have a condition. I might change that later because it's kind of, I've written a little bit of this and it's kind of annoying. But for now, you always have to have a condition of the form, does this equal that? Is it less than? Is it greater than? And then if you're familiar with C, the repeat, that's the equivalent to continue, and break is spelled stop. So these are our approved uses of goto, if you know anything about the goto statement. Okay. Oh yeah, and this is just showing, in C, you have other kinds of loops. And I just was going to show real quickly that there are, ways to recreate those loops in this language. So that's more just, I'm going to quickly jump past this part. And then also, this talk was much longer, and I was going to go into some of the challenges I had with the actual compiler implementation and things like, how to correctly do a loop and not over-optimize so that, because it's important to generate correct code. So I'll just put this up briefly, because if you know assembly, you might point out here that, oh, well, this could be reduced in size by flipping the arguments there and using the branch equals to. But so if you're interested in that, hit me up on Discord. We can talk more about optimizations that I did. And then also, like, if you have a jump followed by, jump to subroutine followed by a return from subroutine, I've optimized that to just do a jump. So I've kind of built some things into the language to produce more efficient code. And then the last thing we need I wanted to show was the inline assembly here, which, I mean, it literally just will take whatever you write and put it out to the assembler. So this is a way to, like in my case, I wanted this program to start at 800 hex and then jump to the main subroutine and then jump back to, using the DOS vector, I think that's called. But, if you potentially you could write this for another 6502 based architecture and you would have a different memory layout and you would need to do something different there. So that's another reason to support inline assembly. And yeah, so this is what the whole thing looks like. I know it's kind of a lot for Hello World, but if you think about it, that's all you need to print out Hello World in this language. And that's kind of proof that it's running. I used Ample, which was presented, I think, last year. The emulator there. And I won't go through it again, but that sample is actually on the GitHub link. And also this game that I wrote, Warship, is also on there. And I wrote my first version of this battleship inspired game to kind of play around with the A2 ASM. And yeah, more GitHub links. And then I rewrote it in A2 to kind of get a sense of the development experience for A2. And if I'm being honest, it wasn't great. Writing compilers is hard. And I think it was very buggy. And so, well, actually, I guess I fixed a lot of the obvious bugs, so that's good. But it still doesn't provide like a lot of helpful information. It's basically like invalid program. And then I was a little disappointed that if you look at the stats here, the line count, it required a few more lines than the actual assembly. And then the compiled output, it's nearly, almost double the size of the handwritten assembly. And I think there's a lot of room, though, for improvements because I haven't done a lot of the optimizations that I could have. For example, a lot of the generated assembly for that looks like, if you're modifying a variable, you would have to, call a store A or store X instruction. And then, if I'm going to do something else with that, I immediately load back in that value. So that's just, wasted thing. So that's something that you could go through the code generation step and, look for that and then just not call the load operation. And that might save us the extra 2,000 bytes right there. But I accomplished a long time dream. Wrapping up here, I was able to run this my Lucy. This is my 2E unenhanced, just your regular 2E, and it's running the code, the A2 port of Warships that I wrote. And so I added here some proof. And so yeah, it's great to write a non-trivial programming language, create one, write a compiler for it, and have it running on actual hardware. Yes, and then check out the GitHub link. The short link is just a2lang.com. I guess this is like the YouTube like and subscribe moment. Go to my GitHub and click the star. And this video is sponsored by Javier's retro brighting shampoo, which I've been using, as you can tell. But no, seriously, check it out. I think Hackfest is still going. Maybe write an A2 program and submit it for that or something. And if you have any suggestions, features, there's Discord afterwards, but GitHub has issue tracking and things like that. So I don't think I have time for all of this, but yes, there's a lot of stuff we can do to add more. I think adding more useful compiler error message is probably the biggest thing. I have some other ideas, the standard library, but I think I'll stop there because I think we're out of time anyway. So thank you guys. Thanks KansasFest and Apple II forever.